These next examples are just integral series tests, but we're going to do a little bit harder integrals in this case. So to set this up, we're going to let our function be y equals x over x squared plus 1. And then we're going to set this up as our limit. The limit as a approaches infinity of the integral from 1 to a of x over x squared plus 1 dx. So we need to use substitution here because we have that plus 1 in the denominator. So the way we're going to set up the substitution, we're going to let u equal the denominator expression. So x squared plus 1, that makes du equal to 2x dx. I want to get that x dx. Maybe I'm just going to highlight that, the x dx all together. And to do that, I'm just going to divide both sides by 2. So du over 2 is what we're going to replace the x dx with. Okay, so then we're going to set this up as a limit as a approaches infinity of, and because we're using a substitution, I need to state my bounds as x equals 1 and x equals a, and then my substitution is going to be u, I'm going to replace the x squared plus 1 with u. The x dx I'm going to replace with du, and I'm going to put the 1/2 just on the outside. I'm going to anti-differentiate this, so limit as a approaches infinity. This is going to end up being 1/2 log u, and our bounds are going to be x equals 1 to x equals a. So now, working this out, my area, so this is my area. So my area is equal to the limit as a approaches infinity of 1/2 log, and instead of u, I'm going to replace my u with x squared plus 1. And because I'm back to x's, I can just use my bounds as 1 to a. Okay, so substituting in now, I'm going to end up with limit as a approaches infinity, factoring the 1/2 out. I am going to end up with log a squared plus 1 minus log of 1 squared plus 1. Okay, so there's my integral. I'm now just going to substitute my infinity into this expression, so I end up with 1/2. This becomes log of infinity squared plus 1, so that's log infinity, minus this becomes log 2. Well, log infinity is infinity, so we end up with infinity minus log 2 divided by 2. That's still going to be infinite, so this is divergent, which lets us conclude that, therefore, the infinite sum is also divergent. In example 7, we have this integral, or sorry, this sum of ln n over n squared, and we're going to do this as an integral test. So we have to figure out what the y is going to be. So the y is going to be log x over x squared. Now, when we set this up for the integral, we have to recognize what kind of integration we're going to apply to this. So we're going to start at n equals 2 to infinity. And in this case here, I should set it as a limit first. So that's a limit. That's a limit as n as a goes to infinity from 2 to a. And when we set this up, we need to figure out what type of integration to use. In this case here, this is not a standard integral. We can't use power rule. We could try substitution, but substitution doesn't seem to work in this case. So we're going to have to try parts. So when we try parts, we have to figure out which parts are which. So we need to choose a dv that is the most complicated that we can anti-differentiate. So in this case here, it looks like the 1 over x d is going to be and 1 over x squared is going to be our dv. So we're going to let our dv equal dx over x squared. Okay, that makes our v term negative 1 over x. Our du term, our u term is going to be the log x. So u is equal to log x. So our du is equal to 1 over x dx. Okay, so then I'm going to use my parts formula. So this becomes the limit as a approaches infinity, and the integral is going to look like this. So I have two parts to it. I have my uv, so in this case my uv is going to look like this. So negative log x over x. Okay, so that's the first part of it, minus the new integral. It's going to be the integral from 2, and sorry, I should put my bounds in since the bounds for this is going to be from 2 to a, minus the integral from 2 to a of our v du. So I'm going to end up with negative x squared. So that extra negative is going to make this positive. I'm just going to write this as 1 over x squared dx. Okay, so working this out, so limit as a goes to infinity, negative log x over x from 2 to a, plus, this is going to work out to be negative 1 over x, and the bounds of this are going to be from 2 to a as well. Evaluating this, in fact, I can maybe, since I've anti-differentiated that, I can just put my bounds at the end there. So I'm going to plug in my a value. So now I have my antiderivative function. I'm going to plug in my a into this expression. So I'm just going to factor the negative out. So log a over a plus 1 over a, and then that's going to be minus log 2 over 2 plus 1 over 2. So this, and maybe I'll just make sure you're clear where that negatives come from. I've taken the negative out of this expression. I've put it in brackets here, and I put a negative in front. So that's where that negative came from. So now I can just let the a value be infinite. So my area is equal to negative log infinity over infinity. Well, we know as a limit that this is going to be equal to 0 plus 1 over infinity. That's equal to 0 as well. And then minus log 2 over 2 plus, this should be in brackets here, plus 1/2. So this works out to be a finite, this ends up being a finite sum. Okay, so we know that the area is finite, therefore convergent. Okay, and so we can say that the sum, infinite sum of n equals 2 to infinity of log of n over n squared is also convergent.